Welcome back, students, to the session on communication, analog communication, unit number 5, that is noise. Okay, in last session we have studied the signal to noise ratio. Now this session we need to study the noise factor of amplifier in cascade, commonly known as the Friis formula. Okay, so now observe this diagram given below, that is two amplifier 1 and amplifier 2 are connected in cascade. Amplifier 1 adds a gain G1, noise factor F1, whereas amplifier 2 has gain G2 and noise factor F2. Okay, these are two noise amplifiers are connected in cascade. Here is the overall noise factor of the system, and the output of the first amplifier 1 is nothing but F1 G1 K T0 Bn, where F1 is the noise factor, G1 is the gain of the amplifier. Similarly, we need to get the output of the amplifier 2. Here now available noise power at the input of the amplifier 2 is nothing but Pni2 equal to F1 G1 K T0 Bn plus in bracket F2 minus 1 K T0 Bn. This is the input to the amplifier 2. Now we need to calculate the overall output of the system. Now consider the output of the second amplifier, that is noise output of the second amplifier, PnO2 equal to gain of the second amplifier G2 multiplied by input to second amplifier, that is Pni2, whereas Pni2 is nothing but F1G1 KT0Bn plus in bracket F2 minus 1 KT0Bn. Okay, now consider this G1 and G2 is nothing but the overall gain of the system, so it is referred by G equal to G1 into G2, and did the overall noise factor be F. Okay, this will get the overall noise power output that equal to FGKT0Bn. Now solving the above equation, this equation and this equation for the overall system output of the noise, then we'll get the F equal to F1 plus F2 minus 1 upon G1. This F is nothing but the overall noise factor of the system, here F1 and F2 is only limited up to F1 and F2 because only two amplifiers are connected in cascade. Okay, now when multiple amplifiers are connected in cascade, in that case the formula of the overall system can be changed, and this like this: F system equal to F1 plus in bracket F2 minus 1 upon G1 plus F3 minus 1 upon G1 into G2 plus so on, and this is commonly referred as Friis formula. Okay, so in theory paper there may be a theory question on this Friis formula, derive the equation for the Friis formula, or one simple example will be asked on the Friis formula. So you must understand the formula, or you can remember the formula of the Friis. By making G1 large, contribution of the other stages can be made negligible. Now we'll take a simple example based on that Friis formula. Here is the statement is given that a mixer stage has a noise figure of 20 dB, and this is preceded by an amplifier that has noise figure of 9 dB and can be available power gain of 15 dB. Calculate the overall noise figure referred to the input. So here first of all note down what is given. The given data is nothing but the noise figure. Okay, so noise figure of a mixer is of 20 dB. This preceded by an amplifier, means first is in this amplifier is there whose noise figure is of 9 dB and the available power gain is of 15 dB. Now this is our Friis formula for this one, at F equal to F1 plus F2 minus 1 upon G1, where F1 is the noise factor of this amplifier, F2 is the noise factor of the mixer stage, G1 is the power gain of this amplifier. Okay, now this formula is nothing but in the form of noise factor, and we know the difference between the noise factor and noise figure. Noise figure is nothing but the noise factor in dB, so hence noise factor are itself in power ratio, so we need to convert this dB into the power ratio and then put the values in the formula. So this can be possible by taking the antilog of the given data. So here F1 is given that 9 dB. So antilog of this thing is that equal to 10 raised to 9 divided by 10, which is nothing but 10 raised to 0.9, which is equal to 7.94. Similarly, for 20 dB it will get 100. Similarly, for 15 dB it will get 31.62. Okay, by putting this value we get the overall noise factor of the system is 11.07. Now after that we need to get the noise figure of the overall system. Hence for this one we need to convert this 11.07 into the dBs. Okay, and this can be possible by taking the 10 log of 11.07. It yields approximately 10.44 dB. Okay, so we need to understand the procedure of calculation of these things. Now the noise temperature. Noise temperature is measured generally for the antenna and low noise amplifier. Now consider here NIN is the external noise from the source, that is NIN equal to K TSBN, where TS is the equivalent noise temperature of the source, usually 290 Kelvin. Now we may also write NE equal to K TEBN, where TE is the equivalent noise temperature, the element that noise temperature of the element, that is with noise factor F and with source temperature Ts. Now equating these equations, that is KTEBN, that equal to in bracket F minus 1, means that is noise factor of the system minus 1 into KTSBN, where K and Bn get cancelled. So overall equivalent noise temperature of the element, that TE, that equal to F minus 1 into Ts. Okay, you should remember this relation, because based on that relation small example may be expected in the theory paper. Okay, now this noise temperature formula can be extended for the number of elements are connected in cascade, and also known as the Friis formula. So here Friis formula can be expressed in terms of noise temperature, where TE system is the overall noise temperature of the system, and TE1, TE2 are noise temperature of the individual stages. Hence, TE system, that equal to TE1 plus TE2 upon G1 plus TE3 upon G1 into G2 plus TE4 upon G1, G2, G3 plus so on. Okay, so this can be extended for number of elements are connected in cascade, and this is in the form of Friis. Now we need to understand the term noise bandwidth. Okay, since any communication system has a front end filter, the noise bandwidth of interest is the bandwidth of this filter. Receiver filter transfer function is h of f. Ideally it should be rectangular, as shown to transmit the same power as of real filter. Okay, so generally this filter is in the form of rectangular form, because cutoff frequency we should to put into that one. Noise bandwidth Bn is adjusted to get the same. Okay, and that is Bn equal to pi by 2 multiplied by Fc, where Fc is the 3 dB cutoff frequency. Okay, now up to this one we studied the basic fundamental noise terminologies. Now applying this basic fundamental terminologies onto the particular communication system. Okay, so now we studied AM system, FM system, as well as PM system. Okay, so here we need to study the noise behavior of AM system. In this unit we need to study the applicable noise on the AM systems. So in that AM systems we need to understand what is the behavior of the baseband system in presence of noise. Then we need to study what is the behavior of DSB-SC, SSB-SC in presence of noise. Okay, from this section we do not expect a numerical, only theory will be expected, and this is fixed for 7 marks in the end sem examination. Okay, so we'll continue this part in the next session. Thank you.